Hi there, it's Mrs. Tollison. As promised, here is the video review for fossils, continental drift theory, and the theory of plate tectonics for the test on Friday, the 4th. I'm going to go through this. It's probably going to be maybe 10 or 15 minutes. I'm not exactly sure how long it's going to take to get through it, but at any point if you need to pause it to look over what's on the slide, please do. And if you want to have your review sheet next to you so you can fill that in, that might not be a bad idea. So here we go. Okay, we first started off talking about fossils. Fossils are just preserved evidence of ancient living things, and the scientists who study prehistoric plants and animals are called paleontologists. We talked about in class that all living things that die do not form fossils, and that's because the conditions have to be exactly right for fossils to form. More often than not, fossils of the hard parts of organisms like shells, bones, teeth, etc. are more likely to form because the soft parts like tissues, muscles, things like that decay too quickly to form fossils. Very rarely, extremely rarely, circumstances where you get an entire organism that can be fossilized either by getting trapped in amber, like for small insects, ice, like some mammoths have been preserved in ice, or sometimes animals have fallen into tar pits. Body fossils is a special name for any part of the actual organism that has been preserved. For example, if it's the entire body, teeth, bones, the shell of something, etc. Anything that's an actual body part of the organism is called a body fossil. There's another group of fossils, trace fossils, which are a lot easier to find because a single organism can leave many traces behind, but they only have one body. Trace fossils provide evidence of once living things. They can include things like leaf imprints, footprints of an animal, any trails or burrows or nests that an organism had, or even sometimes they can find fossilized feces of once living organisms that can prove that they were there and possibly what type of food they ate, things like that. There are several different ways that fossils can form. As stated previously, fossils can be the actual remains of a plant that is or animal that's been preserved in amber, ice, or tar pits. Sometimes a fossil becomes petrified or turned to stone when, over time, after the organism has been trapped under the soil, the original material that made up the organism is replaced by minerals from the dirt and rocks that surround it. And that takes long periods of time. An imprint is any impression that is formed when an organism is buried and squeezed between layers of sediments, leaving a thin film of carbon. We looked at some fossils and saw some fossil imprints of what look like leaves or ferns. Sometimes this can happen with fish and other organisms where it just leaves kind of a perfect outline of the organism. An imprint, though, can also be a footprint that's been left behind by an organism. A fossilized mold or mold fossil occurs when an organism that has been buried decays over time, but enough time has passed that a perfectly preserved empty space in the shape of the organism is left behind. So it's like an empty cavity in the exact shape of the organism. A fossil cast forms only after there's a fossil mold. So first there has to be a fossil mold, then a fossil cast can form when the empty space in the mold is filled in with minerals or sediments that harden to create a shape that's the same as the shape of the original organism or whatever parts were created by the mold. So here's some images of different types of fossils. So here we have a couple of imprint fossils. We've got a fish, and you can see a lot of detail in there because it was pressed between layers of rock or layers of dirt, which eventually became rock. Here we've got some fossilized, what look like dinosaur footprints. This is a mold fossil of a trilobite. You can see that there's an impression, it's indented here, and that's what the mold is. It's an indent. Then this is a cast fossil of some type of shell, so there had been an empty space, and then that empty space filled in and became a cast. And here are a couple of petrified fossils. This looks like a dragonfly here and petrified wood. So over time, all of the original living material that made up this dragonfly and made up this tree were replaced by minerals, so they are become petrified. And there's a special type of fossil that we talked about too in class. It's called an index fossil. This is a fossil that can actually be used to tell the age of the rocks it is in, because index fossils, there has to be three things for something to be an index fossil. It has to have been occurred over a widespread area. It had to have existed for a very short period of time. Not that it lived for a short period of time, each individual organism, but that type of organism only existed for a short period of time in the geologic time scale. And then also it had to have evolved or changed rapidly. So you knew there was kind of just a little snapshot of time where the organism looked that way, and that makes it an index fossil. There are three main types of rocks: igneous, metamorphic, and sedimentary. We don't really need to go into detail about what these types of rocks are. You'll learn more about that in 8th grade. But we talk about it because sedimentary rocks are the types of rocks where most fossils are found, because they're sandwiched in between the layers of rocks. And there's a few steps in the fossil formation, which is shown in this picture above. The writing is a little unclear, so I'll go over that. First, the organism has to die, and in this picture it says an ancient crocodile dies and sinks to the bottom of a river. Then over time, the organism is buried under a layers of sediment. You can see that here. And at the same time it's being buried, the soft parts of the organism are decaying. So you can see in this picture it looks like mostly just the skeleton remains. None of the soft tissues or the skin or the muscles or anything are left behind. And then over millions of years, the hard parts of the organism can be replaced by minerals and preserved as a fossil. And then this picture shows a couple of other steps where that eventually the rock erodes, it's washed away, and maybe the fossil is exposed on the surface of the rock, and that's how it would be discovered by a paleontologist. The geologic time scale describes the units of time that divide Earth's history, and Earth's history has been divided into 4 main periods called eras. These eras or eras are not of equal length. I mean, some of the pictures we looked at in class had the geologic time scale going from left to right, but I found this one that goes bottom to top. So starting longest period of time ago, longest ago was Precambrian, and that was, even though it looks small here, Precambrian was actually the oldest and longest era of time in Earth's history. Then there was the Paleozoic era, then the Mesozoic era, which was when the dinosaurs were, and then the Cenozoic era, which is the era that we are currently in today. Continental drift theory was proposed in 1912 by Alfred Wegener. He proposed that the continents were once all part of a single landmass called Pangaea, and that the continents had slowly drifted apart to where they are today. And Wegener collected several pieces of evidence to support his theory. He noticed that the continents looked like they fit together like puzzle pieces. He also realized that similar fossils were found on continents that were now very far away from each other, and there really was no other reasonable explanation for how they could have traveled such long distances. Like the Mesosaurus, it was a freshwater reptile. It was not reasonable to think that a freshwater reptile would swim all the way across the ocean, which is seawater. Besides, it was a small animal, and that was a really long distance for it to have traveled. So he believed that the continents that contained the Mesosaurus fossils had once been next to each other. Fossils of a plant called Glossopteris have also been found in present-day Antarctica. Glossopteris is a fern. It's normally found in temperate climates right now, so this is proof that Antarctica must have been closer to the equator in the past. Unfortunately for Wegener, most scientists of his time did not believe his theory because he could not explain how the land masses moved. So that was the big fault of his theory. He couldn't explain it, and he didn't think it was really his job to explain it. In the 1960s, scientists discovered evidence that helped to prove that Wegener had been right all along. As scientists were studying the bottom of the ocean, they realized that the ocean floors were spreading apart and that new ocean crust was being formed at the mid-ocean ridges in a process called seafloor spreading. This evidence led to our current theory of plate tectonics, which states that the Earth's crust and upper mantle, which make up the lithosphere, as we learned before with the Earth's layers, is broken up into large slabs called plates. And these plates move slowly across the Earth's surface because of convection currents in the mantle. And convection currents in the mantle, we talked about this a little bit before. Convection happens because if you look down here, this material in the mantle, it's a solid, but it's a solid that slowly flows, very, very slowly. It takes a long time. So this material in the mantle that's down here closer to the core, it gets heated up and it starts to rise up through the rest of the mantle, and it gets towards the top of the mantle and it cools off and it starts to sink down here back towards the core where it heats up again, and it gets heated up and it rises and it creates this circular motion. So depending upon how these convection currents move, like it shows this convection current's moving this way and this one is moving this way, so then it shows, so that would pull this plate in this direction and this plate in this direction away from each other. And then we have this convection current turning in this clockwise direction, and this convection current going in this clockwise direction here, no, sorry, going counterclockwise here. So that is pulling this continent in this direction, and it's pulling this continent in this direction. So that's pulling them towards each other. So depending upon the direction of the convection currents, that can control which direction the plates are moving that are riding on top of them. We got one last slide. There are three types of plate boundaries. There are convergent boundaries where two plates move towards each other or collide. So convergent plates collide or crash into each other. Divergent boundaries are where two plates move away from each other or divide. So divergent plates separate or divide, move away from each other. And transform or transform fault boundaries are where two plates move horizontally past each other or slide past each other. So transform or transform fault boundaries slide. So again, convergent, they're colliding or crashing into each other. Divergent, dividing or moving away from each other. Transform or transform fault or sliding past each other. Thank you for listening to this and watching this video. I encourage you to watch it more than once to help you study for the test. And if you have any questions, please let me know.